Okay, so this is direct sum of the again of the two direct systems, and I have a map K here everywhere, which is again given by the 2 by 2 matrix, and I claim that I can define this K just by the formula. So I define this by the following matrix: E, 1 minus E, 1 minus E, and E. So it's easy exercise. Okay, so it's easy exercise that actually all the squares are the same. So the square is commutative. Just multiply 2 by 2 matrices. So, and also another easy exercise that I leave it to you to, if you compute the K squared, you get the identity matrix. So in particular, you know that the K is an isomorphism, and inverse for the K is just the K itself. So that's an isomorphism between two directed systems. But in particular, it means that homotopy limits are also isomorphic, right? If the two directed systems are isomorphic, then homotopy colimits are isomorphic. So the homotopy colimit for this diagram is the sum of the two homotopy colimits with the x's and 1s, with the x's and 0s. So the answer here is x, and the answer here is, of course, y plus z. So the conclusion from this is that x is isomorphic to the y plus z. We have this decomposition. And now I want to fix some notation. So let me fix notation h with the index y from the direct sum of the x to the y, and the same with the z from the direct sum of the x's to the z. So these are the maps. So remember that we defined y and z as homotopy colimits, and if you just look at the distinguished rank of homotopy colimits, there is a map from the sum to the homotopy colimit, right? So the second map in the distinguished triangle defining homotopy colimit. So I don't want to write these distinguished triangles to save some time, but this is the maps that you get in those triangles. So now I have the following square, commutative square. So I take the two copies of the infinite sum, say one copy and another copy. Right. So here I have the map h sub y plus h sub z to the y plus z. Here there is a map with components g and g prime to the x. Here the same. The same direct sum. And the map between these two direct sums is given by the direct sum of the matrices K. And here, of course, there is a projection, like in the top row, there are these two maps to the homotopy colimits. The same is, again, two maps to the homotopy colimits, but for this direct sum. So essentially, this is projection P, which is the, and the second map is, of course, 0. So that's the square that we have. And this map G and Gy is just defined, since we know that there is not isomorphism. So this is the isomorphism between these two objects in components. Now I can look at this commutative square and take recomposition of this, say, go like this or go like this, and take recomposition with the map Ui. So I get two identities.
What is G and G prime? What is G and G prime?
So these two objects are isomorphic.
Yes.
That's the isomorphism written in components.
Yes, so it is Z isomorphism.
Yeah, that's that isomorphism, but I choose the kind of names for the
Yes.
components of this isomorphism. So I have, from the commutativity of this square, I have the following formula, which I'm going to leave to you as a little exercise in this linear algebra with infinite matrices, essentially just take this commutative square and take the UI, which is either the embedding in the first component or in the second component with the index I. And that's what formulas that you get. And then I'm ready to define maps F and F prime. So F, by definition, is the composition of the H sub Y U0, and F prime is by definition map which is the composition of the H sub Z U0. Okay. There is a clear observation that if you take a composition of the P U0, you will get just the identity. Right? Since this is just a map to the homotopic limit from the direct system where I have X everywhere and the identity map. So then, combining this kind of three formulas and two definitions, I'll get the following: that the composition of the G and F is E, and the composition of the G prime and F prime is 1 minus E. Right? So just the special cases of these two formulas when index I is equal to 0, and I know that PU0 is identity, and I plug in definitions of the F and F prime. So then the composition, so let's look at the composition. I go from the X using F and F prime to the Y plus Z, and then back using G and G prime to the X. So look at this composition. But if you just, again, exercise multiplying two matrices and using these two formulas, so this composition is identity of the X. So this thing is just 1. So this map with components F and F prime is the inverse from one side to this map. But this map is an isomorphism, so this map is actually inverse from the other side. So which means that if I take the composition in the other order, F, F prime, G, G prime, and so this was the composition going from X to the X. This is the composition that goes from the Y plus Z to the Y plus Z. But you can compute this, a standard linear algebra computation, the so-called rank 1 matrix. So that's what you get, and this is supposed to be the identity on the Y plus Z. Okay. So in particular, the conclusion that I need is that the composition of the F and G is 1. So I have GF is equal to the idempotent E, and the composition in the other order is identity. Hence, I check two properties of the splitting for the idempotent E. Okay. So I'm going to erase this part of the statement. So do you have any questions? Okay. So next proposition, which is a little bit computational. Well, the previous one also was computational. So it says the following. If I have S inside T, a triangulated subcategory, so triangulated subcategory, in which idempotence split, so then S is thick. Remember that thick means that this is closed under direct summons. So the standard property that if you closed under splitting idempotence, you closed under direct sums. Let's take this direct sum. So suppose I have a x plus y and draw canonical projections and embeddings for the x and for the y. So I'm going for the x, the projection is p, the injection is u, and for the y, the projection will be called q, and the injection I'm going to call. So since I have the property that the composition of the P and U is the identity on the X, just at the moment I just essentially using the properties of the byproduct. So I get myself an idempotent UP, since in the middle there is PU, which is identity, is equal to the UP. So the idempotent that I want to consider is composition of the U and P. Since I know that every idempotent splits, I can claim, so there are maps G from the direct sum of the X and Y to some object Q. So notice that this object Q lives in the subcategory S, right? So we have the property so that idempotents split in the subcategory. And so there's map G, and there's also map F that goes in the other direction from the Q to the direct sum of the X plus Y. Okay. So, and the properties that we have is that the UP is equal to the FG and GF is identity. That's what we get if we apply the definition of splitting idempotent and for idempotent UP. And then I'll do some computations. So I look at the 1 minus UP, compose this with the F, which is clearly F minus UPF, right? So then this is F minus FGF, right? So why this is the case? Because UP is known to be equal to FG. So we have this formula. And we also know that the composition of the G and F is 1. So this is F minus F, really. So this is F minus F, 0. So this composition is 0. Now let me introduce some notation. So let me call map T to be by definition composition of the P and F, right? So then the formula that I just proved, I can be written as follows. Maybe I'll squeeze it here. So then the previous formula is the same as the F is equal to the product of the composition U and T. Okay, but F is mono, right? Because for the F we have GF equal to 1. So F is mono, and when we have a composition of two maps such that the composition is mono, then the first map in the composition has to be mono. So T is mono. Now I have the following. So T is mono. I look at the composition of the T, G, and U. So plug in the definition of T. So I'll get P, F, G, and U. Now F, composition of F and G is UP. So this is P, UP, U, which is using that the PU is the identity, is just the identity. Right, so identity on the X. So this is not just a mono, this is a retraction. So T is a retraction. Or by general statements about in category theory, if you have a map which is mono and a retraction, then this is actually an isomorphism. So T is an isomorphism. But now, if you look at the T, so that was the composition of the F, right, and the P. So this is a map from the X. This is a map from the Q to the X, right? So this map T is from the Q to the X. Hence, X is isomorphic to the Q. And remember that the Q was in S. So what I proved is that the direct sum on X is actually in the subcategory S. That means that S is closed on the direct summons. So as you can see, and I want to say that this is probably the only non-trivial statement that we, for example, can prove using homotopic limits in intermediate categories. So I don't know how to do this without homotopic limits. So the theory of homotopic limits in intermediate categories is quite limited, but still useful for example, for this proposition. So in particular, we have the following robbery. So any localizing subcategory of a triangulated category is thick, which again wasn't obvious from the definition. So remember that localizing means that this is closed under all products, and thick means that this is closed under direct sums. In fact, you can assume a little bit less, so you can assume that this category is not localizing, it's closed under countable products. Okay. So we prove that. So this is essentially the end of the section, and before I start the new one, there will be two sections that kind of at the end we get a non-trivial result that I think is quite a very interesting result. The goal essentially is to show the following: that if
why do we have this corollary? So
this is just it immediately follows from the proposition. So in the proposition we have a subcategory which is in which idempotent splits.
yes.
And before that, we proved that if we have countable products, then idempotent splits.
Yes, and localizing category.
Has all products, at least all countable.
Yes.
Yeah. So now what's the goal? Because in the next two sections we're going to develop some theory. It won't be. I want to have a clear goal before we do this theory. The goal is the following. So if A is Grothendieck abelian category, do I need to remind you what the Grothendieck abelian category is? Nice abelian category. It has two properties. The property which is sometimes called AB5, which means that if you take directed colimits in ordinary sense, of course, not homotopic, then they exist as functors. And the second property is that in this category there is a generator. So that's the Grothendieck abelian category. And examples are essentially everything that we see in algebraic geometry and representation theory. So if you have category of modules, that's Grothendieck. If you have category of some quasi-coherent shapes or just OX modules on a scheme, this is a Grothendieck abelian category. So in this case, the property that we have is the following. So if then L inside the derived category of A is localizing, then L is closed under say directed limits. So which means more precisely the following: that suppose I have a say directed system, let's call this maybe G. So from some I to the complexes in the A, right? So this is directed system, meaning that I is a directed category. So then if Ci is in the L for every object I in the category watch I, then if you take just the standard directed limit in the category C, in this category we can take this right? In the DA, this doesn't make any sense, it doesn't exist, but in the C, it exists, right? So this is in the L.
I don't understand what is C? It is a function.
Here?
Yes.
So sorry, this is supposed to be G. So this is G. Yeah, that's supposed to be to this. So this is a directed system, meaning this is a function from a directed category to the category of complexes.
Yes.
I assume that every object in this directed system is in the localizing subcategory. Then if I take the directed limit, just in the category of complexes, right? This is where this makes sense. And then this is again an object in the L. So this is kind of probably the main and the most important property of the localizing subcategories. So the method that we're going to prove this is kind of a little bit roundabout. We're going to develop the, well, first of all, if you take a trivial observation that if you have localizing subcategory, this is closed under a homotopy equivalence, right? Because it's closed under direct sums. So two objects in a triangle is in the L, so this third object, which is homotopy equivalent, has to be in the L. So we're going to develop the general theory of the homotopy. Well, and this is here the problem. So this is not just natural numbers, this is any directed category, directed set, right? So this is the more general statement. So that observation about homotopy equivalence is definitely not enough. So the idea is to go in two steps. Define the general theory of homotopy equivalence that works in the derived categories. So derived category is kind of much richer than just any derived category. When you say that derived category is time grid, you forget a lot of data. So it can work actually in complexes. So you can, in the D of A, you can define the theory of homotopy equivalence for any diagram, directed diagram. And then prove the theorem that homotopy equivalence in the categories Grothendieck actually coincide with just the ordinary equivalence. So then you get this result. So if you want kind of hard challenge in this course, well, can you prove this without any theory of homotopy equivalence, just directly? So the statement makes sense directly without any homotopy equivalence. So maybe there is a proof that doesn't require this developing of this theory. We're going to do this lecture and also next week. Okay. Okay. No. I'm not sure how to move this. Okay. Okay, so, oops. Okay, so that is the plan. And now with this plan, I'm going to do two sections. So first, 3.4, and this is kind of a little bit as a reminder. I'm going to call this directed limits and colimits. So mostly for what I have in mind, I need colimits, but there's of course dual theory for the limits in abelian categories. So I'm silently assuming this course that you know something about abelian categories. So in this section, I allow myself to skip maybe several steps, but actually the steps I'm going to skip are usually quite simple, so you can do the proofs by yourself. Okay, so let me introduce a subsection and call this subsection Roos complex. So that was introduced by Jacques-Éric Roos. I think in the paper was published in 1961, so it's quite old mathematics. What's the idea? So here I assume that A is a abelian category with exact products. So A, abelian category with exact products. So this is called AB4 star. Property having exact products is sometimes called property AB4 star. So then we define, this is how we use Roos complex, so we define kind of the write the right functor for the inverse limit, but the assumption is that I only have AB for star. I don't assume that I have, for example, injectives. So define this in A and show that it is right derived functor of the limb if A has enough injectives. So well, there are two assumptions about the A. The first assumption is exact products, and then you can define the derived limits without using derived functors or injectives, or you can assume that in the category you have enough injectives and then just use machinery of derived functors and derive this functor. And if you have both assumptions, they can actually coincide. Okay, so let me assume that I have a inverse system. So G from the I opposite. Oh. So I opposite to the A is an inverse system. So for this inverse system, I'm going to define the Roos complex. So definition, the homological Roos complex. Of course, there is a dual theory where I have homological Roos complex, and this is responsible for the left derived of the direct limit. So I'm going to call this, since the last name is so simple, it's just 4 letters, I'm going to call this Roos of G. So this complex is defined as follows. The objects or terms of this complex are, so the Roos K of G, so K is just some positive integer, is equal to the product of the G of the I0. So here I assume that I have kind of this sequence of maps of the length K. So these are maps in the category I, and the product is parameterized by these sequences of the length actually K plus 1, since I start with a 0. And then I just take the zeroth term and compute G over the zeroth term. So that's the object, and the differential dk. So this is a differential from the Roos K of G to the Roos K plus 1 of G. This is defined as the alternating sum. So the sum over J between 0 and K plus 1 minus 1 to the J, D with the in the J, K. So for J equal to 0, so I want to define D0K now. I define as follows. So this has to be a map of Roos K of G to the Roos K plus 1 of G, so D K0. And since this is a product, I can kind of specify this map if I can specify the composition with the projections. So there's a projection which I'm going to call pi I0 I K plus 1 to the G I0. And here from the Roos K, I take projection with indices I1, I2, Ik. So I start with 1 here. Up to K plus 1. K plus 1. And this will be to the G I1. And here we have a map from the inverse system. Right. So if I want to specify this kind of part of the differential where j is equal to 0, I need to specify this composition with the projection, and I say that by definition this is this. So this is d0, and for the positive j, the definition is similar, but actually even easier. So let me say that the map from the root k again, dkj to the root k plus 1 of j. Again, to give this map to you, I need to give you projections, compositions with projections. And in this case, this is just the projection from the root k, but in this sequence of the i's, I skip I with the index j. So this is I0, da da da. I omit I with the index j up to I k. So that's the definition. And of course, I'm giving you some little exercise, and this is alternating that the d squared is really 0. Okay, so I said by definition R k of the inverse system J to be the cohomology of the root complex. And you can think about this as the kind of higher directed limits, right? For example, now we have several trivial observations. A 45, say, observation, maybe, okay, several simple things, observations. So the first one, what's R0 of G? So if you look at the complex, well, this has to be the kernel from the root 0 to the root 1. So root 0, you have just product over single objects. Here, this will be the product over the maps, I0 to I1, right? G, I0. But if you know some category theory, you know that you can present directed, well, in this case, any limit, right? You can present as an equalizer between products. So that's exactly what you have here. So this is directed, so sorry, inverse, inverse limit of G. So in particular, for the k equal to 0, we have what we want. So I'm saying just if you have assumption just a before with a star, so let's consider this Rk as the natural generalization of the inverse limit. So this is my definition of the derived functions of the inverse limit in this case. Okay, so then the second easy observation. So if I have short exact sequence of the inverse systems, so this is short exact system of inverse systems. So then I get the short exact sequence of the root complexes, which more or less immediately follows from the definition of the root complex and the property that the products are exact, which I assume. So then, in particular, we see that this system of functors Rn, and for n at least 0, is a delta functor. Right, so that's the delta functor on the abelian category of the inverse systems. And 3, which can be also verified directly from the definition, is that when you apply this to the product of the directed system, then this is just the product of the Rn of the GI. So it commutes with all the products. So three very simple observations. I leave this as an exercise. Okay. So then I have proposition, which I probably also mostly going to use as an exercise, because this is when I indicate one important step, the rest is very easy. So any G in the category of directed systems, which are going to shorten just all A to the I opposite, so can be embedded into F, which is another directed system, such that this F is R asymmetric. So R with the index n applied to the F is 0 for any n which is at least 1. Okay, so proof, which won't be a complete proof, so just the idea of the proof. The idea of the construction of this another system F. So we define functor, so fix object I in the indexing category I and object little a in the abelian category A. So define directed system or functor depending on these two choices, I and A. So from the I opposite to the A by the following rule. On the objects, this functor, so object is some object J from the category I, so this is defined as the product over all arrows that you have from I to the J, and you take A. So you take the product of A with itself as many times as you have, as many arrows you have between I and J. This is the definition of this functor on the objects, and I also need to define this on the morphisms. So let me assume that beta is a map, say from the J1 to the J2, right? So then I have the product of all arrows from I to J2 A and product I to the J1 A, right? So I'm defining quaternion functor, so this is how it goes. So I need to define kind of, for a given map beta, I need to define this map. Right? If I so this is of course F I A J, and this is J2, and this is F I A J1. And the map I'm going to define will be F I A of beta. But again, since this is a product, I have projection. So it is convenient to call this projection P alpha to the A, where alpha is in this notation just really some arrow from I to the J1. So I need to specify this composition with projections, and I do this as follows. Here I take projection for the map, which is composition of the beta and alpha to the A. And here I take just the identity map on the A. Right, so since alpha is on this form, I can take composition with the beta, and this will be a map from the I to the J2, right? Composition of the alpha and beta. There is a corresponding kind of element in the product here, which is A. So there is a projection to the A. And here this is just the identity of A. So this, to specify this map, I need to specify this composition, and this is by definition given by this. So this is how you define, this is kind of the key idea. Once you define these factors that you're going to use, the rest I'm going to leave you a simple exercise, which is kind of, if you think about this exercise, it's really silly. Because all the maps that you have in the definition are just products of the object, and all the maps are just essentially identities. So I claim the following. So if I take the Roos complex of this functor that I defined, right? So this is homotopy equivalent, to the A 0, 0, 0, and the rest are just zeros. This is, of course, for any I and A. So you can just take this functor, plug in this into the definition of the Roos complex, you get quite explicit complex, and you can explicitly write the homotopy, just some simple combinatorial exercise. So in particular, I have what I want. This is acyclic with respect to the Ruska homology. So the Rn for the Fia is equal to 0. Okay, and then I can embed any diagram G into the product of such functors. So I take the product over all objects I, Fia. And again, to specify this embedding, I need to specify composition with the projection. Right? And in this case, sorry, this is not A, this is GI. Right, and I can specify this map, for example, if I plug in the definition of the Fi GI. So equivalently, to define this embedding, so I have a map to the product over I. Yeah, say I write this Fi GI. Yeah, so let's take this diagram, right? And to specify this map, I evaluate this diagram on some object J, right? So let's evaluate everything on the J. So then here, the projection will be to the product I to the J, J of I. And now, to this product, I have a map, since this is a directed system. So this is a map given by, so if I have some projection, so this is just a map given by the map in the directed system. So we can verify this is indeed a monomorphism, which again, still exercise that immediately follows from this definition. And this, I want to say that this finishes the proof of the proposition. So, the conclusion is that it follows from proposition that the Roos homology Rm of the system G is isomorphic to the nth derived limit of the, so what we consider at the moment homological complex, so this will be inverse. Yes. G. Okay. This is the test of your knowledge of the classical homological algebra. How this follows from the proposition.
Because we can write the resolution of a functor, which is acyclic.
Yeah, but here you're going to write, from the right hand side, you want to use the injective resolution.
No, to compute the derived functor, I can use any resolution.
Yeah, but the resolution that we constructed is acyclic for this functor, and we don't know that this is acyclic for this functor.
Yes, yes.
So that's a problem. So the observation follows from the Grothendieck theorem on effaceable functors. Effaceable functors. Do you know effaceable functors? Well, this is a piece of general theory that I never have time to do in the general category theory class. So let me just briefly remind you what we have. So definition. So the follows from the proposition by the following line of the arguments. So we have a definition. So let me recall the definition of the effaceable functor. So a functor, an additive functor. So an additive functor, say f a to b between abelian categories is called effaceable. If I have the following, for any object A, or maybe let me call this large A. For any A, which is object in this category A, so there is a monomorphism, so there is mono U from A to some other object M, such that f of u is 0. So theorem by Grothendieck this is from the famous Dohaka paper, so it is from the 57. It says the following, that delta functor, let's call this Rn, since we already have Rn, in our notation, is universal. No, sorry, the delta functor such that all this Rn's, so Rn is effaceable for any n positive, it is universal. So if you look in the Michael's textbook on homological algebra, there is something like this, I think, in the second chapter, and this theorem by Grothendieck is actually given as an exercise. So actually you can do this as an exercise, not very hard. But if you fail, I can give you a reference. So for the proof, you can look at in the Grothendieck's paper in Tahuko journal, and I think this is statement 2.2.1. But I think it's possible to do this as an exercise. It's not really hard. So then, by the proposition, it follows that the Roos functors Rn are effaceable, right? Because we have even more. Right? We can always embed into something such that the f of m is equal to 0, hence f of u is equal to 0. Hence, this delta functor Rn is universal, and the direct limit, any derived functor is universal, and the universal functor is unique. Hence, we have this coincidence of the two functors. So it indeed immediately follows from the previous proposition if you can know this little theory that works in the abelian category.
Can you repeat, please, how it follows?
Well, we proved even more than required by the definition, right? We proved that we can have an embedding such that this f of m is 0, hence f of u is 0.
Yes.
So the condition of the Grothendieck theorem is satisfied for the delta functor r to the n.
Yes.
Right? So then the r to the n is universal.
Yes.
And the derived functor is always universal.
Yes.
So you wipe that second chapter. And the universal functor is of course unique. Hence these two functors coincide.
Yes. But how we know that the right derived functor exists?
I assume that if both definition makes sense, so for this definition I need exact products, for this definition I need enough injectives, if the both conditions are satisfied, then they are the same. And if you have only, for example, one condition, another condition, you can use this theory or the other theory. So it happens, I think, not just in this example, but it happens in some situations where you can kind of define a homology by hand without using machinery's injective functors. For example, in the shift theory, you have check complexes, or you also have Wadema's complexes. Both complexes don't require any injectives. You just want some sort of explicit constructions. And here this is the same. You can think about this as kind of one explicit construction, such that in a special case, this gives you the right limit. And why I wanted to repeat this kind of piece of elementary homologic algebra about Roost complex, because actually this is how homotopy limits are defined. So this works in any abelian category. Now take as an abelian category complexes, take the Roost construction, and that's by definition what's called the homotopy limit in the category complexes or in the derived category. So actually, you can think about this as the rules defined homotopy limits and colimits many decades before it was introduced in homotopy topology. Okay. So maybe it's time for a break, so let's take it on this break.
В общем случае, если нет достаточно инъективных объектов, нельзя никак резольвенту написать вот из каких-то таких функторов f и a для пределов.
Ну, здесь что вы имеете в виду под этим? У вас инфоточно получается, если у вас есть вот эти функторы R, да, для экспоненции цикличности.
Да, а для этого она не ациклична для обратного предела.
Если у вас сейчас зависит, как это будет определяться цикличность. Чтобы сказать о цикличности, вам надо сказать, например, что первый производный функтор зануляется, да, на этом объекте. А если у вас нет инъективных, то вы его не определяете.
Ну, можешь сказать о цикличности, что если есть три короткая точная последовательность, я применил к ней этот функтор, то получилась тоже короткая точная последовательность.
Ну, можно, да. Сейчас вопрос такой, что будет ли ацикличный, который, грубо говоря, в смысле руса, ацикличный в смысле просто предела?
Да.
Ну да, конечно. Ну, потому что вы уже можете просто написать длинную последовательность, ну, взять короткую, точно взять длинную, и там русовские гомологии занулятся, она циклична. Ну, значит, просто останется короткая точная последовательность. Поэтому это само собой следует. Да, ну это в таком способе это то же самое, да? Вы просто построите резоленту ацикличную в смысле руса, она считает русовскую гомологию, и она будет цикличной для Рима, да? И она посчитает производную функцию элементов, да? Ну вот так. Можно удобно эксперимент Grothendieck. Можно так, да.
Мы уже не исследуем книжки Нимана по триангулированным категориям.
Ну,
где?
это только первых
Да,
двух
первых двух.
Ну,
Первых двух лекциях где-то.
ну, первых двух глав, да, это
Да.
первые две недели.
А что читать по остальным?
Ну, комплекс русских, кстати, тоже есть у них в аппендиксе А. Они там где, я не помню, какой там раздел, но там, в общем, как раз два раздела, посвященных производным этим самым пределам, да. Один был часть комплекса русского, он просто это как называет, но конструкция точно такая же. То есть это тоже есть немножко не правоблизующие категории, ну, вот эта теорема следует там статья, более-менее не следует книжкам. Сейчас я готовлю. Николай, вы говорите, что вот он душами занимается, просто усилие, все такое, да? А вообще вот эта двойственность Верди, ну, которая не реконструктивна, просто для пучков. много каких-то концов, да, будет ответ на например. Она сложно оказывается, кто
Над любым кольцом.
ну, хотелось бы, это сложно учиться или не очень?
Я вот про это в книжке, про которую читаю, там только в аппендиксе одном приводится для колец.
Конечно, его не место.
Да.
Ну, хорошо, пусть, конечно, его не место, да. Но там просто, насколько я понимаю, в государственности или технологии, там будет такое условие, что этот f с нижним факториальчиком, он должен быть гармонически конечный, да?
Да.
Просто вот это условие, что означает?
И вот просто про двойственность Вердье, как бы про конструктивные пучки только сейчас начал изучать. Совсем
Нет, это конструктивно, это просто пучки.
Просто по пучки я даже не слышал, что там про двойственность Вердье.
Нет, конечно, в смысле это есть. Ну, ладно, мне казалось наоборот. Сначала двойственность Вердье просто для пучков модулей, а потом уже конструктивность появляется. Ну, то есть такое утверждение, что у вас есть два точки пространственных, вопрос, которые компактны, между ними непрерывное отображение, оно идет сырое, как бы R, прямой образ компактный носитель, точки с производной категории нормы над X, производной категории над Y, ну там фиксированное кольцо, разумеется, какое-то, да? И тогда для нее существует право производной R с верхним факториальчиком на производной категории.
Да, это...
Ну, это и есть, по-моему, двойственность отдельно, что называется. Я просто не очень понимаю такое условие, что функтор логически конечный. Оно, например, как связано с условием, что этот функтор f с нижним факториальчиком, но производный, разумеется. Право производных f с нижним факториальчиком, например, коммутирует с предельным. Это следует из гармонической конечности, это гармоническая конечность следует из этого, какое условие сильнее, как они связаны. Ну, просто если, грубо говоря, это гармоническая конечность следует из сохранения по пределу, ну, что совершенно не очевидно, может быть совершенно даже неверно, то я могу, если знаю, как грубо говоря, все время элементарно доказать, и когда стоит требуется, нужно просто следовать теоретически из того, что сделано на курсе.
В чем утверждение? Что... как связана конечная когомологическая размерность и...
Да, то есть я могу доказать двойственность Вердье, грубо говоря, ничего не делаю, но мне потребуется условие на функтор другой, мне потребуется, чтобы f с нижним факториальчиком коммутировался по пределам.
Да.
Вот тогда я могу сказать, что существует f с верхним факториальчиком. Но это не то же самое, что классически называется двойственностью Вердье в учебнике технологии. Поэтому я как бы интересуюсь, как эти условия связаны.
Я вот там вот это утверждение видел в двух видах. Там вот в одном случае f с нижним факториальчиком строится из d минус в d минус.
Ну да, наверное, да.
И там для этого, видимо, требуется конечная когомологическая размерность.
Потому что он d минус попал, да?
Да. Это вот такое утверждение якобы в тезисе Вердье в таком виде доказывается. Но тезис Вердье не смотрел. А у Гельфанда Манина, и они ссылаются на Кашвара Шапиру, Shifts of Manifolds, там с факториальчиком с нижним из d плюс бьет.
Меня не d плюс d минус не интересует, я хочу просто d. То есть, мне кажется, я могу легко доказать, что во-первых, я с нижним факториальчиком определен на всей категории, не нужно как d минус на d плюс. А во-вторых, если коммутировать с произведениями, то тогда существует двойственность Вердье. Ну, посмотрим, когда мы до этого дойдем, пусть я могу сделать логическое замечание, а вы посмотрите, насколько это соотносится с топологией настоящей. Ладно, давайте продолжим. Yeah, so now I want to essentially finish this section give you a topological remark. So let me call this shift interpretation of the Rus complex. So if you have any partially ordered set, so call this P, so then we can always extend this by adding initial germinal objects. So P is the union with the P hat, 1 P hat, and 0 P hat. So the 0 is initial in the P hat, and 1 is terminal. So maybe in the P there is initial or terminal object. We don't care about this. We add additional initial and terminal just by hand. This is essentially just for notation. Okay. So then we can define Alexandrov topology. Alexandrov topology on the P by saying that U, which is a subset in P, is open. By definition, if the condition that Y is in the U and X is less or equal than Y implies that X is in the U. So then, using my notation, I can say that the intervals from the 0 to the X, so which is open on the left and closed on the right, this is the basis of the nth notation is also U of X. Or you can also rewrite this as the Y. These are elements in the P such that Y is less or equal than X. So this is the basis of the topology. So many partial ordered set I can introduce topology. And why I need this? Well, first of the curious observation, geometrical theorem. So let I be a directed set. Then there is an equivalence of categories. Then there is an equivalence of categories. So we can take directed systems, which is just A to the I opposite, and you can take the sheaves on the I. So sheaves with the Alexandrov topology. So directed systems are really just examples of the sheaf theory, but on very specific kind of space with a kind of a little bit artificial topology. The proof again will be only a sketch. I'm going to define two functors, and when we have a definition of these functors, it's very easy to see that they give an equivalence of categories. So in one direction, functor phi from the sheaves to the directed systems, and if I take phi, compute this on some sheaf F, and I want to compute this on the element X, I just say that this is by definition the value of the sheaf on the open set U of X. So then the map in the directed system, so phi of F on X to the phi of F on Y, right? So this is just induced by the inclusion that the U of X is included into the U of Y for X less or equal than Y. And the sheaf in the other direction, psi, so this is the sheaf now from directed systems to the sheaves on the I with Alexandrov's topology. So let me now call the directed system M, I opposite. So, and then I just define that the psi of M, if I want to, so this is supposed to be a sheaf, so I want to compute this on some open set U, so it's enough to take U of this form, so it's enough to define, at the moment I define this as a pre-sheaf, right, and then it turns out that this pre-sheaf is actually a sheaf. So it's enough to define this only on the basis, so enough to define this on the Ux. But I can write this by definition, so this will be just S sub x, which is the element in the product of the M sub x, so x is in the U, such that S sub x is equal to the mu x y S sub y, x is less or equal than y. So in other words, you can just say that what we have defined here is just the limit of this directed system M, but not for the I, but restricted to the U. This is more or less the definition of the limit. Inverse limit, of course. Yeah, and the map, right, so if I have I, the inclusion of U, of V into U, then psi of M of U is mapped to the psi of M of V. So this is restriction of the limits. So I'm not going to verify that the compositions in both orders are identity, but with these definitions, this is again not very hard to do. So why this is relevant to what we do? Because we have very simple observation. Very simple observation, again, if you just look at the definitions of this function, that if we look at the global sections on the space I, which is a directed set of the sheaf, which is psi of some directed system M, right? And then, since this is a global section, there is no restriction to U. U is just the whole space, right? This will be the limit of M. So the global sections for this topological space is the same as the limit for the directed system. And we immediately from this, just by say, taking the derived functors, conclude that the sheaf cohomology for this topological space and the sheaf which is psi of M is the same thing, so isomorphic to the derived functors of the limit of M. So derived limits are just really sheaf cohomology for a very specific topological space. And with this picture, I can give you an interpretation of the Roos complex. So verify this. I think this is obvious, but I actually, to be honest, never checked the details. That if you want the Roos complex of M, this is the global functions, global sections applied to the Godemann's resolution of the psi of M. Right. So have a nice cyclic Goleman resolution, then you apply global sections to this, and as a result, you get the Roos complex. So this is the way to invent Roos complex that you haven't seen this before. You use this Alexandrov's topology, you interpret the derived functors for the inverse limit as the cohomology of the sheaves. Then you know that you can also compute cohomology of the sheaves by using Godemann's resolution. So you take this complex, and actually this won't be something new, this will be the complex that the Roos used as a definition. Just, I think it is a curious remark, and I also want to use this remark as an analogy. So this analogy and the remark in this second subsection, which is the Mittag-Doppler sequences. So another important notion from the elementary homological algebra in the abelian categories. So here, for the sequence, I fix an ordinal, so gamma is an ordinal. And I want to consider J, which is, I want to specify gamma, J is identical gamma, the set of all ordinals less than gamma. Definition: a sequence of length gamma, well, it's just a functor G from the J opposite to the A. So this is a sequence of length gamma in some abelian category A. So this sequence is called, for shortness for Mittag-Doppler, I'm going to call ML. So ML sequence, ML conditions, etc. So if we have two conditions, so for any pair I greater than J, the corresponding map from the Gi to the G of J is epimorphism, and the second condition is that for any limit ordinal say J, so the map from the G of J to the limit of the taken over I is less than J, G of I is also epi. Okay. So that's the definition, and it's maybe if you see this for the first time, it's not clear why this is a reasonable definition. It is kind of standard in homological algebra. There are actually variations. There are a little bit more general definitions. For example, you require this to be epi not for all the maps, but only for kind of sufficiently high ordinals, which is enough to the conclusion of the most of the theorems. But the remark here is that if you have so ML condition is similar to Flaby condition for sheaves. Well, the problem is that this is kind of, I want to say this is only similar. I don't want to say that this is exactly the same thing, because in general this is not the case. So you have the equivalence of the two categories, and you want to say that ML condition on one side is the same as the Flaby condition on the other side. That's wrong. But it is, and this of course depends heavily what category you consider. So for example, if you consider the simplest possible example, A is just the category of the abelian groups, so then Flaby is exactly the same as ML. But in general, they might be different. But at least you have the motivation. So remember that in the Flaby, a Flaby condition you can frame it as follows. So the sheafless Flaby, if you have two open subsets, right? So there is an induced map on the sheaves, and this is an epimorphism. So here this kind of similar thing, and if you use this functor psi phi, you'll see that this is translated to the epimorphisms for the sheaves, but you need to check a bunch of conditions, and not all of them are satisfied. So this is not something bijective in general for a category, but this is in abelian for category of abelian groups, this is true. And I want to say one thing without a proof. So which is, oh, since it's not exactly the case, and this ML condition, we can think about this as something like condition defining objects acyclic for the inverse limit. So we want it, the ideal theorem will be something like this. You take a metaphorical sequence, you compute the R1 of the limit, and you get 0, right? That would be an ideal theorem. Unfortunately, without assumptions, this is not the case, but I think the best theorem you can show is the theorem of Roos from 2006, which says the following. So let A be an abelian category with a generator, satisfying AB3 and AB4 star. So remember that AB3 means that you have coproducts, AB4 star means that you have exact products. The condition that we already saw today. So if, say, G is the beta-Klöffler sequence of length omega, so then this is indeed acyclic, so all the derived limits are equal to 0. So there is also a theorem in the Niemann's book in the appendix A, I don't remember which section of the appendix, where you have similar theorem, but he assumes that, I think instead of the generators, he assumes that in the category A you have enough projectives. So you have something like AB3, enough projectives, then he shows that AB4 with the star is satisfied, and you also have this result, but not only for omega, but for any length which is less than you have products. So you have, if you take a product or some ordinal, you do some gamma. You can take the sequences of lengths up to gamma. Yeah, and this theorem has an interesting history. I think it was first published in 1961, but there was a missing condition. Missing condition that this category has a generator. And then I think in 2001, Niemann and Deligne wrote a paper, a counterexample from the 1961 theorem in homological algebra, where they constructed the counterexample to this theorem without assumption that we have a generator. And then 5 years later, this Roos published a paper which kind of was answer to that paper by Deligne and Niemann, where he corrected this statement and he actually proved a lot more statements. So you can, for example, look at this paper by Roos. It's quite interesting, but it's kind of not what you do in this course. It's not about the categories, it's about the abelian categories, and the technique is quite advanced. So, for example, if I want to prove something like this, I probably need at least 1 week for this. I don't want to do this. Okay. So this section was kind of just a reminder about direct limits and abelian categories and some entertainment comparing this with the sheets. Maybe some explanation why the definition of the meta-Klöffler sequence is a reasonable definition, and how this can be thought as an analog of the Flaby condition. Now, I want to go to...
Does it have this theorem greater equals than 0? So even for n
Of course, right. This doesn't make sense. So for any positive n, of course. So all the direct limits are 0. That's just a fact. Okay, so section 3.5, homotopia. Limits and limits in direct categories. Well, I want to remind you of several kind of basic operations that are called truncations in the direct category, and there are 3 types of truncations. So first there are two truncations. So in the Grothendieck category, of course, you don't have any truncations. This is something that you have in the direct setting, and more generally, to talk about truncations, you need T-structure on the Grothendieck category. But in this course, we're not going to use T-structures, we will only discuss something in the direct categories. So, definition for good truncations. I take complex, say, X, that's in some derived category, some abelian category A, and also I fix some integer n. And then there is sometimes people say good truncation to distinguish this with the other types of truncation, or just say truncation for shortness. So good truncation from above. From above. So the notation will be tau less or equal than 0 applied to x. And this is just a complex, and I think it's easier to understand this if I just write this, what terms it has. So it has all the terms as before, up to n minus 1. At the x position, you write the kernel of the differential, so this is some sub-object of the xn, and then after this kernel, after position n, you put zeros everywhere. So that's the translation from above. And you can say, well, why is this called truncation from above? It's a natural operation. And there's a dual construction truncation from below. So two good truncation from below. Well, defined very much in the same way. So you'll get on the left zeros until you reach position with the index n, and there you write co-kernel of the d with the index n minus 1, and this is mapped to the x with the index n plus 1, and the rest is the same as in the original complex. So about this definition, I have several elementary remarks. So first one is that from the truncation from the above, I have the canonical monomorphism In. So this is from the tau less or equal than nx to the x. So of course, clearly from the definition, you have a monomorphism from this truncation to the region on the slide. You embed the kernel here, this is just identities, and the rest of the maps are just zeros. So that's mono. And it induces isomorphism on cohomology, so I sub n is isomorphism for any I less or equal than n. And the same is true for the second type of truncations. So there is a quotient map Qn from the x to the truncation from below, tau greater or equal than nx. So this is epimorphism, and it induces isomorphism on cohomology. So this isomorphism for any I greater or equal than n. Simple observations. Another simple observation that you can, for example, consider complexes which have non-zero terms only up to n, so Ca less or equal than n, and consider this as a full subcategory inside A. So this is full subcategory. So then the truncation from above is the right adjoint. Right adjoint to inclusion. This is easy to check. And you can consider the dual situation where you can say that similarly if you consider truncation from below, and then this is left adjoint. So these functors have categorical meaning. This is what I'm trying to say. So left adjoint to the inclusion of the CA greater or equal than n inside C of A. Okay. So then, simple observation is that we can, for example, truncate truncate from above at 0. This is mapped to the truncation from above at 1, etc. So general truncation at the level n is clearly canonically mapped to the truncation at the level n plus 1. It just follows from the definition, etc. So we get a directed system. So truncations in such way form a directed system. So lemma, the complex X is isomorphic to the direct limit of such truncations. Maybe this is one of the reasons to introduce such truncations, right? So when you truncate it like this, for example, we can try to understand something from the complexes which are bounded from above, and then try to show the property that we're interested in is respected by taking the directed limit, and then you have this property for any complex. This is how in applications that could be used. So, yeah, and notice that this is just a computation in the category of complexes. Of course, if you take a direct category, there is no direct limit there. There are homotopy limits, but this is another story. So, and yeah, of course, if you have this statement, as usual, in the category theory, we have the corresponding dual statement. So you can also present X as something which is isomorphic to the inverse limit of the truncations from below, but I also change the index to the minus n. Yeah, and to make sense of this, of course, you need to assume that, for example, in the first line, A is complete. Now A is co-complete. So AB3. And in the second statement, A is complete, right? Yeah. Complete, so we have products and yes. So if you have a complete category or A is co-complete, you have this statement section. Essentially for any kind of truncations, there is a corresponding statement with a limit of element depending on what you have, direct or inverse system. So for the proof, of course, the proofs are also only consider, say, first case. And then you just look at the diagram. So you have truncation at the level n. This is mapped to the truncation at the level n plus 1. Then there is complex X, and there are canonical embeddings I, n, and I, n plus 1. Now, if you suppose that you have some other complex T, right, and you have maps un and un plus 1. So you want to construct a unique map phi. So there is a unique map phi such that everything is commutative. But if you think about this, it is clear, right? You want to define this map, you want to define from some level, right, from some xi, right? So xi to the ti. You just get the truncation such that, well, choose an n large enough such that you don't truncate at the level xi, and then you already have a map. And then for any index, you can choose the corresponding truncation. So I want to say this is actually quite simple. Okay, so this is good truncations, and there are also another version of truncations, and in the second exercise you will see why these are interesting. So brutal truncations also have some applications. So brutal truncations are also called speaker truncations. So definition, as before, I assume that X is some complex. Well, I wrote, I think, derived category, but really what I need is just a complex, so I can as well write C of A and choose an integer. And so then there is brutal truncation from above. So the notation is with the sigma, so sigma is equal to n applied to the x, and we just write this is the same xi if I is less than or equal than n, and 0 if I is greater than n. That's the definition. So you don't write this kernel or co-kernel in those situations. You just write x's and zeros. So you won't preserve the homology at the position n now, but the truncation consists of the objects of the same type as the original complex. For example, if you have something like a complex of projective modules, you take such truncation, you still get a complex of projective modules. The homology might be different, that's a problem, but the nature of the objects is the same. And there is a dual version too, so we have repeat everything, but not from the above, but from the below. So this will be sigma greater or equal than n, xi where I is greater or equal than n, and 0 otherwise. So you can notice the following, again, maybe remark, maybe not. So there are maps from the x, say, to the truncation from above, and such maps are, of course, epimorphisms. And we have, so inverse system with semi-split epis. So truncate at the level n plus 1, map to the truncation at the level n, etc. when you reach level 0. Okay, so I used word semi-split, right? It means that this is epimorphism of complexes, but semi-split means that there is a kind of splitting map in the other direction, but this map doesn't respect the differential. This only splitting on the level of the graded complexes. Of the graded objects. Is it clear, or do I need to write this? So, say phi, just the general definition, from x to the y, so map of complexes is semi-split if, of course, this will be a semi-split epi, but it will be epi automatically. So if you have the following, we have, say, xi, this is mapped to the yi by the map yi. So here there's a differential to the xi plus 1, yi plus 1, differential. Well, this is differential for x, this is differential for y. And this is phi I plus 1. So look at just one square. So the semi-split epi means that there is a map in the other direction. So there is a splitting, say Si, and there is a splitting Si plus 1, and the same is for any I, right? But this S is not a map of complexes. So the square, when you go like this and like this, like this and like this is not commutative, so it doesn't respect the differential. But this is map of the graded objects. And of course the composition, to have a split epi, well, you apply phi, and so I want to here phi and then s phi, right? And we get identity of the y. I think this is right. For splitting epimorphism, is this the right composition of the phi and s? I always confuse myself with this split epis and split monos, because we have left and right. I think this is right. Okay, so that's the definition. So we have epi in the category of complexes. It is not split in the category of complexes. It's only split in the category of the graded objects. And another thing to notice here, which is quite important, if you compare brutal truncations and good truncations. So this is inverse system. But when we consider the good truncations, we get a directed system. So the truncations are from the same side, from the above, from the right. But good truncations form a direct system, and brutal truncations form an inverse system. And that's important. Well, first of all, it's important not to make mistakes, and it's also important if you want to combine them together and get double truncations. But before I do double truncations, I formulate the lemma, which is similar to the lemma of the good truncations. So the lemma is that, let me not say in the beginning that A is complete. And the x is isomorphic to the inverse limit of the brutal truncations, and 2A is co-complete implies that x is isomorphic to the direct limit of the truncations from below and the minus n. The proof is more or less the same, so I'm not going to prove this. And yeah, I want to go with the double truncations. This is a little bit more exotic, but still useful. For example, it allows you to reduce problems from the. You consider some property. For example, you can show this property for a bounded complex. You know this property is preserved by limits of polymers, and then you can prove this property for unbounded complexes. And we can define this as follows. So, again, definition these two parts. I take a complex over Euclidean category A. Now I take two integers, n and m. N is strictly smaller than m. And then I can define two kinds of truncations. So first, so the difference is between parentheses and brackets in the notation. So if I use parentheses and then m, so I can define this as the sigma less or equal than m, and tau greater or equal than, or specifically on the left I have zeros until I reach position n, where I write co-kernel of the differential with the index n minus 1. This is method x with the index n plus 1. And this is the standard complex until I reach xm, and after this I'll get 0. And 2, x with the brackets n and m. This is the other way around. So this is the sigma greater or equal than n, and tau less or equal than x. And again, specifically, this is a complex where I have 0 until I reach n, and the n I have xm, which which I continue until I'll get to the position with the index m, where I have kernel of the differential with index m, and after that I'll get zeros. So these are two versions of the bounded complexes. And notice that I combine them in a very specific way, right? So when I do this, like, well, I don't consider, for example, brutal truncations on both sides. I don't consider good truncations on both sides, because if I do this, I won't be able to write direct or inverse limits. So I'll combine them in such a way that one sequence form a directed system and the other form an inverse system. So let me specify this with more details. So there are epimorphisms from the x to the x with the parentheses n and m, right? So such maps, and also from the x with n and m to the x n prime m prime, such that n prime is greater than n and m prime is less or equal than m. So these two maps are epis, which is clear. So you can, if you use this first type of truncation, so you can see that you can truncate, and there is canonical epi to the truncations on both sides, but which is small. And if you truncate using the second type of truncations, there are monos in the other direction. Yeah, but before I do this, maybe I also specify that there is an inverse system. So in particular, there is an inverse system. So x minus n plus 1. This is mapped to the x minus n plus 1 n. So all the way to the x minus 1, 2 to the x 0, 1. And of course there is a similar story for the other kind of double truncations. So there are maps x and m in brackets to the x, and x and m to the x n prime m prime, and this makes sense if n prime is less or equal than n and m prime is greater or equal than m. So these are monos and there is a directed system. So x 0, 1 is mapped to the x minus 1, 2, and the general term x with the minus n plus 1 is mapped to the x with the minus n minus 1 n plus 2. So the same type of arguments shows that if A is complete, and x is isomorphic to the inverse limit of the truncations with parentheses, and 2, if A is co-complete, then x is isomorphic to the directed limit of the truncations of the second type. Okay. So this is all about truncation that I want to say. Essentially just fixing terminology, notation, and 3 versions of more or less the same lemma in the retrieval proof. So now these truncations, there are several statements, and I think again that if you just write the formulas and do the computations, they are more or less immediately follows. So I don't really want to prove them. Maybe I just fix some notation. So I can consider map Cn from the abelian category to the derived category. And this is just a map. And that just a short notation, you take an object and you put this object at position n. Right? So that's a functor between additive categories. Clearly this is an additive functor, right, from the A to the derived category of A. So you take an object, right, and you form a complex where you have this object A at the position n, and all the other objects in this complex are 0. Yeah, so with this notation, I can formulate the lemma. It's useful to know, but I don't want to do this since it's very simple. So let X be a complex, which I consider as an object in the derived category. I take an integer. So then there are distinguished triangles in the derived category, which are also factorial in the X. So natural in the X. So the triangles are as follows. You take the truncation, so good truncation at the level n of the X. Let's take n minus 1. So n minus 1. So you have the map to the, I have the definition, one for n, one for the n minus 1. Look at the map. You can realize what is the corresponding co-kernel and hence the distinguished triangle. So this will be hence a homology of the complex X. So you'll get one distinguished triangle like this, which is again useful in the applications. For example, we're trying to show something by induction. You know this for homology, you know this for the complexes of the small lengths, and then you derive this property for this complex. That would be a typical application. And there's of course a dual situation where you embed n's homology. And you realize that this is the same as the kernel of the truncation from below at the level n, which is mapped to the truncation from below at the level n plus 1. So proof is a simple exercise. And there is another exercise also. Well, this is exercise because I think this is silly. It's very simple. I don't want to waste some time writing this on the workbook. The exercise that I'm going to give you is not silly, so it's a reasonable exercise. So exercise is the following: that the functor Cn from the A to the derived category is full. This is not silly because you need to understand morphisms in the derived category, some sorts of rules, and you need to show that NU kind of is induced by the honest map in the abelian category. So it's a good exercise, I think. Simple, but it's still good. And one more lemma about this. So, as before, I take X in the object in the unbounded derived category. So then there is the distinguished triangle. One more distinguished triangle of truncations. There is a distinguished triangle like this. So I take a truncation from above at the level n, embed this into the x, and then there is a map to the truncation from below at the level n plus 1, x, and then back to this truncation with the shape pattern. Or maybe I do this proof because I skipped this proof of the previous lemma, and maybe it's reasonable to give a proof of this statement. This is just because, well, I consider this truncation, so let me just write it. So n minus 2. Okay, so if I take the truncation, so the first term in this distinguished triangle, this is what I get just by the definition. So then here I have just the x without any truncations at all. So this is embedding into the xn, and then there is xn plus 1, etc. Right? So clearly this is monomorphism, something that I claimed before, and I can take a quotient. Well, this is a subcomplex of this complex, and I can take quotient, right? So when I take a quotient at the level n minus 2 and upwards, I'll get zeros everywhere. Well, actually at the level n minus 1 also, right? So these are zeros everywhere. So here I'll get, of course, the image of the differential dn. And after that, since in the sub-object I have zeros, I'll get xn plus 1, etc., xn plus 2. So that's the quotient. Right? And I want to compare this with this truncation from below at the level n plus 1. So let me also write this. So this object will have, say, where's xn plus 2? Xn plus 1. Yes, so here I'll get 0. Here I'll get co-kernel of the dn, and then there will be xn plus 2, etc. So this is sub-object, object, this is quotient, and this right column supposed to represent the truncation of from below at the level n plus 1. Okay? So, but here, if you look at this last map, the last canonical map here, I'll get the isomorphism, right? So, here I have all the zeros. So this is the map. So what we really need to check.
Why you have in dn in the third column? Why you have the image of dn in the third column?
Here?
Yes.
Because it's a quotient by the kernel. So this column is the quotient.
Yes. So it is not the truncation.
No, this is not truncation. So I'm taking this sub-object inside X,
Yes.
right? And then I take, so let me maybe write it here, so what I have. So this is truncation, like this is X, and this column is the quotient of the X modulo this sub-object. So then, I can write that I have a distinguished triangle, so I have clearly distinguished triangle like this. Right? This is just a general property. Any short exact sequence of complexes induces a distinguished triangle in the derived category. So this I'll get automatically. But now, to finish the proof, I'm trying to show that there is a quasi-isomorphism, so this is quasi-isomorphism, with the truncation that I want, n plus 1. Right? If I can show that this quotient is quasi-isomorphic to this truncation, then I'm done. I have the right triangle. And what I was trying to say here is that clearly this map induces isomorphism and cohomology everywhere, right? Because, for example, if you go up from this level, you'll get zeros everywhere. So 0 isomorphic to 0. So here, this is the embedding, right? So the kernel of this map is 0, the image is 0, so the cohomology here is 0, the cohomology here is 0. So, and of course, below this map, it's just identity map on the level of complexes. So the only problematic ways where you need to show that cohomology are the same is here, right? Map from the xn plus 1 to the kernel of the dn. But that's a very simple map by the differential to the xn plus 2. So then here there is a quotient map to the kernel of the differential, right? Since the image is contained in the kernel, there is kind of it. So the kernel of the d tilde n plus 1 is precisely the cohomology, right? So if I want to compute cohomology here, this is just the cohomology here. So this is the induced map. And I claim that the kernel of this map is precisely the cohomology. Well, since you take the kernel, but this map is on the co-kernel, this may be the simplest way to realize this. This is the quotient by the image, and then take the kernel. But in the cohomology, you take the kernel, then take the quotient by the image. So that's the same thing. So, okay. So to continue, I want to consider cases where I can reduce homotopy limits and colimits over n that we already defined to the usual limits and colimits. Limits and colimits over n. Yes. So let's start with the colimits. So I assume that A is co-complete. Directed system. Homotopy colimits, I can form a diagram where I take the, that if I consider composition of this map with the canonical injection in the directed map from the Gn to the Gn plus 1. So I'm saying that I don't really want a directed system since I have only homotopy limits over n. So let me change this I. So that's the definition of this map mu as before, and then I know that the co-kernel of the 1 minus mu is the colimit. Okay, so lemma with 3 parts. So first, if A is Grothendieck, then 1 minus mu is mono. Two, if every mu n is split mono, then 1 minus mu is split mono, and 3, if this directed system Gn mu n is eventually constant, so then 1 minus mu is split mono. Yeah, so what I'm trying to obtain here is, I want to say that the map 1 minus mu is monomorphism, right? If this is monomorphism, I can form short exact sequence. Right? So I can consider short exact sequence where I have such object, 1 minus mu, such object, and the co-kernel is colimit. So standard colimit in the category of the complexes, right? Then the short exact sequence induces a distinguished triangle in the derived category. And then I will see that the homotopy colimit of this directed system, homotopy, this directed system, yeah, homotopy colimit, right? Homotopy colimit will be the same as the standard colimit. That's written here. Do you understand the plan? So I want to reduce the homotopy colimits to the colimits. I want a statement that homotopy colimit is equal to the colimit. And I do this by looking at the short exact sequence. So that's the plan, and this is why this lemmos of this type are so important. For example, well, I'm not sure what you know about the Grothendieck categories. Essentially, the statement is that if you have a Grothendieck category, then the limit doesn't have any derived functors, right? So, for example, here this is the colimit doesn't have derived functors, so this is the Milner's situation for the colimits, and I'm saying that there is no first L1 of the colimit. But if you don't know this theory, or if you don't know that in the Grothendieck categories colimits are exact, or filtered colimits are exact, you can give a direct proof of this, right? So the direct proof is something like this. Consider some map alpha from some test object y to the direct sum. And you assume that 1 minus composition is alpha is 0, and you want to show that this is monomorphism, so we want to show that alpha is equal to 0. So then you can look at the following diagram. So I want to write all the maps that I have on one diagram. So there is y with the map alpha to the direct sum. So here there is a phi, which is a map to the product of the Gn. Then there is a map mu that I consider to the, again, direct sum of the Gn. And there is somewhere Gn embedded with the map from the coproduct, which is Un. So here from the product there is map which is a canonical projection pi n, and then we can take the composition of the phi and pi n. I'm going to call the composition Pn by definition. So by definition Pn is pi n phi. So, and the property that I use from the Grothendieck category in this proof is that phi is monomorphism. So phi is mono since A is Grothendieck. So you need to use something about Grothendieck categories. So I'm going to use this property. Okay. So this is just a diagram of the maps that you have. So since we have this assumption that the composition of these two maps is 0, I can as well write that alpha is the mu alpha. So then alpha n, which is defined as a composition of the Pn and alpha, then alpha n is equal to the Pn mu alpha. I'm just taking composition with Pn from the identity that I already have. Okay, so then if we look at the definition, so in the definition we have that this composition of the, say, Un and mu is this thing. So then I can write something like this. The composition of the Pn plus 1 mu Un is equal to the composition Pn plus 1 Un plus 1 mu n. Right? Just the way we defined that map mu, and I take composition with the Pn plus 1. But of course, this composition of the embedding and the projection, this is just the identity. So I can also take a precomposition with the Pn, So I have Pn plus 1 mu Un Pn. This will be so this will be mu n Pn, right? So since this is just identity, I take composition with Pn, I get this, but now this is identity. So the formula is Pn plus 1 mu is equal to the mu n Pn. Now if I take again composition with the alpha, I can write the following. That composition of the Pn mu and alpha. So this is mu n minus 1 alpha n minus 1. This is for n positive n 0 and n is equal to 0. This is previous formula in which I take composition with the alpha. So in particular, alpha 0, which is E0 mu over is 0. And by this formula, we see that the alpha n, which is just this composition of the so Pn mu and alpha that we have on the left hand side. So the alpha n is the mu n minus 1 with the alpha with the index n minus 1. So all these alpha n's are equal to 0. And if all the alpha n's are equal to 0, let's all remember that the Pn was the composition of the pi and phi. So pi and phi alpha is equal to 0 for any n. But now pi's are just projections to in the product. So if the composition with the projection is equal to 0, then it means that the map itself is equal to 0. But since we know that pi is monomorphism, we can conclude that the alpha is equal to 0. And hence the claim. Now that's a proof, but I don't know. I can just rely, for example, on your knowledge of Grothendieck categories and say that this you already know this, that in the Grothendieck category co-limits are exact, hence there is no kernel. Yes, this is monomorphism. Because if there were the kernel, that would be the L1 of the co-limit. Okay, and the 2 and 3 I'm going to leave as an exercises. Okay, so corollary. So let G be a directed system of complexes. So then automatically if A is Grothendieck, then 1 minus mu is mono. 2, if every mu n is semi split mono, then 1 minus mu is semi-split mono. And of course the third property, if G is eventually constant, then 1 minus mu is semi-split So the parts 2 and 3 are straightforward exercises, like in the previous lemma. But for the part 1, I want to comment. There is a very simple observation that if A is Grothendieck,
What is the difference between the previous lemma? So,
the difference is that now I consider directed systems of complexes, not just of objects of the category A. That's the difference. And for example, to reduce, say, part 1 to the previous lemma, I need the following observation. If A is Grothendieck, then the category of complexes is Grothendieck. Well, for limits, I think this is quite easy. For colimits, this is quite easy. If they were exact, they're still exact. But how about the existence of a generator? So if you know that you have a generator in the A, you also need to produce a generator in the category of complexes. Well, you can consider complexes of the form you have in G, identity G, and the rest are just zeros. So say they put this into position. And it's an easy exercise to show that such complexes generate C of A. So there's a family of generators in the category of complexes, and then you can take the coproduct over ON to get a generator in the category C of A. And for the 2 and 3, there is actually no much difference in the proofs.
what is eventually constant? What is eventually constant?
Well, it means that up to some point, all the objects are the same and all the morphisms are identities. There is stabilization.
Yes.
Yeah, so finally, the conclusion why we need these lemmas is the following. So if conclusion of the corollary is true, namely that this map, well, here we have additional information, semi-split monos, but at least condition that these are monos, then we can do the following. We can form short exact sequence, right? So this is, I was saying before, as a motivation why we consider this. You'll get short exact sequence like this, and any short exact sequence give you a distinguished triangle of the derived category. You'll get a distinguished triangle. But notice that in this distinguished triangle, so the first two objects and the map between them is exactly the same as the definition of the homotopical limit. Right? So hence, we can identify this with the homotopical limit. And, well, homotopical limit of this thing is precisely the same thing as this usual colimit in the category of complexes. So this is isomorphism in the derived category or quasi-isomorphism. Okay, so I'm thinking almost out of time. So this will say for today. Maybe there are questions about this last conclusion. Yeah, I was trying to say that the homotopical limit is the same as the limit, right? And I give you an example of the three possible conditions where this is the case, because we have monomorphism, right? And since this is a monomorphism, we can write short exact sequence like this, go to a distinguished triangle, and notice that this kind of object in distinguished triangle so the same as homotopical limit by definition. So we can reduce homotopical limits to the usual limits, and that's the simplest possible case of that statement that I announced before the previous section. I wanted to show that they have a localizing subcategory. It is closed under the filtered colimits or directed colimits, right? And I see that this is the case for the diagrams of the simplest possible form, where the diagram is just natural numbers. but it is true in a more general setting, and to show that it's true in more general setting, we kind of need this special case. So, but the general setting is for the next week. Okay, so I finish with this. Continue